hope that you're going to tell us what you're going to talk about and then talk about it.
Oh, well, a couple of things. The first thing is I've got a new career. I'm a caretaker for a geriatric dog with a broken leg. So my dog Lonely Wolf took a tumble down the stairs, and I've learned a whole lot of new skills that I didn't have before. It's very interesting. It's very focusing. I was staying home anyway, and now I get to stay home and work on little projects that I have on the computer. I just take a portable with me where I'm taking care of the dog and sitting him out in the sunshine and helping him get well. So it's been kind of interesting. Other than that, I've been working on Qiskit and quantum computing like usual.
Wow.
It's still a very interesting time. It's still very up in the air. It's kind of like you're waiting for Edison to invent the light bulb all the time. There's many layers to it. It's not going to be one invention, but you're very much, at this stage, you realize that a whole lot of little inventions have to come along for this all to work and turn into a commercial proposition. And, it's already a commercial proposition in many ways. The number of startups being formed that are going to provide the perfect quantum computing development environment. It's going to subsume everything and it's going to work with everything. The number of startups and the amount of venture capital being pumped into these companies is pretty astounding. So if you look around, you're going to find them. The number of papers, it used to be, in 2009, 2008, 2009, when I was writing about this stuff for Dr. Dobbs, I had to pry information out of people. And now it's like there's more papers in a week than I can read on this subject. I mean, more good papers. There's more crap than you can carry away with a shovel. But there's more good papers on the subject and new things being thought about in terms. The quantum computing it's not just about quantum computing. It's kind of like the wave of quantum physics right now. It's the sexy part of quantum physics, like the way Laurie was what would you call it, drafted from Drosophila research into fourth programming back in the 80s. It's like, it's drafting a lot of physicists because there's these neat jobs for companies like IBM and Honeywell and all these other little companies, big and little companies looking at quantum computing right now. So a few weeks ago, IBM, back in March, IBM was supposed to have this big event face-to-face in the Catskills, and they were going to wine and dine us. It was really interesting, and I was invited at the last minute. It's mostly aimed at young people, but they'll take a few old farts. And so I got the honor chair in that regard. And then, I booked my flight, and then Monday they canceled the event because of COVID. And so I got my money back from the flight and everything like that. So there's no problem like that. But they haven't had any real live events. So recently they had they're figuring out how to do online events. And one thing they had was this quantum challenge. And the quantum challenge consisted of 4 days of working on 4 exercises. You could work on them. You had all 4 exercises from the start. You could work on them at any pace, but they were giving you 4 days. And support was basically the IBM Qiskit Slack channel. And so everybody was, it's like 4 days, it was 4 times 24, 96, or what is it? How many times 4 times 24? 96 hours of sleeplessness, so they're frantically exchanging bits of information with people and trying to figure out these exercises. One of them involved Morse code, strangely enough. It's pretty funny, the test, that the examples you had, they were Jupyter notebooks. Does everybody know what Jupyter notebooks are? Is there anybody who doesn't know what a Jupyter notebook is? Okay, a Jupyter notebook is you can start in Python a Jupyter notebook program, and it reads the Jupyter notebook that you've written, which is written in XML. You don't actually write it physically in XML. You always use Jupyter notebook to compose your notebooks. You can type in live Python. There's cells in it. Cells can be text, cells can be images. They're just like vertical cells, one after the other. And you can have text, and then you can example with text. And you can say, run the cell, and the state of the Python machine changes as you run cells. And you can reset the Python virtual machine that's running. in the Jupyter notebook. And basically it runs on your own machine as a server, and a lot of companies like IBM, when they have tutorials, the tutorials are Jupyter notebooks. They're live. You can run them while you're logged into their website, and there's a Python virtual machine in the back end servicing you, and you can reset it and start again from the beginning of the notebook, and you can close it and it frees the Python virtual machine. So these Python Jupyter notebooks, and you worked through them and you did the answer, and it evaluated your answer and scored you. It had a backdoor to the server that was keeping track of your score and whether you had correctly answered the problem. And there was one of them that basically it was about quantum encryption, and the joke was that when you decrypted the quantum encrypted message, what you got was Morse code. Then you had to decrypt that, So I sat there writing the decryption program for the Morse code, and I said, "What am I doing?" And I just sat there because I knew the Morse code from Boy Scouts, like you guys were saying, It's like, I knew the so I just sat there and did it with a pencil. I just figured it out with a pencil. That I typed in the answer, and I passed that part of the exam. And then the fourth one was just a mind bender, a quantum gate, an operator. You might call it a microcode operator. They call this stuff quantum assembly, but it's really quantum microcode. What they're calling high-level algorithms now are what are really going to be the quantum assembly code of the future usable commercial quantum computers. And so this quantum microcode, the unitary operators, the definition, they're a matrix. The state of the machine is a vector. The unitary operator represents a matrix whose dagger operator against the original matrix is 1. In other words, it's a reversible operator. Okay. So an individual operator. So they give you a unitary in the form of a matrix, and of course Qiskit, the Python library, the huge Python corpus with all kinds of third-party things like NumPy and everything drawn into it, and SciPy and everything drawn into it. Qiskit, which is IBM's offering, which allows you to do prepare quantum computations for the real hardware, or prepare them for the simulators that are there on your machine or in the cloud or whatever. And they also you can apply it to third-party backends. A lot of people have written third-party plugins, so you can use their stuff with the competitors of IBM. So you can use their stuff with IBM's Qiskit, because Qiskit's open source, which is why I'm working on it, because it's open source and it's just lovely to work on that. And so you had to take this unitary and figure out how to optimize it so they scored you for how many gates it took to carry it out. In other words, you can make a unitary operator, a hypothetical unitary operator, which is kind of one instruction in microcode that actually requires thousands of the actual basis gates that the processors support to carry out, because they have a very limited set of operations they can do. As a matter of fact, all the IBM ones can do is identity reset, controlled not, and U3, which is rotation in three-dimensional space of the qubit, okay, of its mathematical model. So to map your high-level unitary operators, they give us a unitary operator that required thousands of gates to implement, and they scored them, and it was like, you were charged like 1 point for a U3 gate and 10 points for a NOT gate, because that's roughly the cost in terms of time to carry these things out in the processor. You're supposed to optimize somehow this circuit so it returned the same result, was effectively the same operator, disregarding global phase, as everybody who knows trigonometry knows what I'm talking about, that it was the same operator, except it used less gates than if you took the pure matrix and threw it at the quantum computer compiler and stuff like that. And man, the anguish and the all-night sessions, and everybody figured this out. And IBM had figured it out, that the lowest, the joke was, you got it, just simply doing it, you could easily get to a score of like 1760 or something like that. And the idea is the lower and lower score. And then you got past that and you jump down in the 300 or 400s, and so you had to get it under 1600 to have passed the test. I got mine down in the 285. IBM had figured out that the lowest you could get it to was a score of 46. A little smartass in South America got it down to 45, past what the IBM engineers have been able to do. It was a truly international exercise. It was amazing. There was 1,750 participants online. About half of them were from India, which gives you an idea of what's going on within this industry right now. So it's a really, there were China, Saudi Arabia, Egypt, Africa, South Africa, every country in Europe, Russia, China, everybody. was there. Iran, everybody was there. And it's really awesome how this field is taking off. I don't know if it's taking us to a brave new world or to 1984 or what it's taking us to, but it's, as Yogi Berra said, we're lost, but we're making great time. And, you know, so that's kind of what's happening for me in quantum computing at the moment. The other thing about it, in terms of my personal involvement, is that, of course, you know, I'm one more crank theorist in a society, the Fourth Interest Group, that is rife with crank theorists and was founded by a crank theorist himself, you know, Charles Woehr. As you know, Charles Woehr was telling me in 1990, in 1989, I did an interview in Santa Rosa or Santa Clara at one of those big events that Moore was speaking at, and we sat down at lunch, and Dr. Dobbs, editor, and the assistant editor was there, and we had a big round table talk. Dennis, you were there, weren't you? Was Dennis there at that round table talk in '89? I forget. It seems to me you were. Yeah, Mitch Bradley was there, certainly. And we had a big round table talk. So in 1990, Dobbs had me do a follow-up interview with Moore, and he was saying, you know, in the future, computers are going to be smaller, but they're going to be all over the room, and they're going to be inside things. You know, in 1990, he's saying this. You know, he was seeing the Internet of Things. You know, and as I've written before, it reminds me of a science fiction story. I think it was Harlan Ellison or somebody like that wrote this story about this guy who had X-ray eyes and incredible, you know, could see anything. And as he got older, his eyes got farsighted, and so he had been like a great circus entertainer up to that time. But as he got older, like he'd be describing distant mountain ranges to people inside the circus tent, and it wouldn't really impress them anymore. And that was Chuck Moore. You know, it's that he was seeing so far in the future, it made absolutely no sense to anybody who was listening to him. And the things he saw, he said, Intel, you know, he was wrong about the commercial aspect of it because he didn't understand business at all. But he said Intel has forfeited the future, and he was right at a technical level. His point was that their processors they were making were so complex they were utterly unsuited for the Internet of Things. I'm now translating what he was saying, you know, 30 years later with 2020 hindsight, what he meant. But really, of course, Intel saw that, and of course, ARM came along and stuff like that, which are more, you know, better designed for these things. But he was right that the architecture they were pursuing and putting every dollar into at the time was utterly unsuited for where computing was going, which was that there were going to be little handheld things and things inside refrigerators and microwaves that needed very little processing power, and they needed a lot of communication, you know. So he definitely saw it. So in line with that, you know, the theory of the, you know, the guys describing distant mountain ranges. This is a paper I submit. I'm going to show you a paper I submit every year, a piece of it that I submit every year to the Gravity Research Foundation. And the Gravity Research Foundation was founded by one of the biggest cranks of all times. And this guy, his sister had drowned in a pool. And so he got on a warpath against gravity. And he was, you know, and he was a millionaire, and he funded all this foundation, the Gravity Research Foundation, so that he could defeat gravity, you know. And so he died, and the money was left endowed. So they sort of changed it into a foundation that every year offers a award, $4,000 award for a good paper about gravity. So I enter every year on the pretext that it's about gravity, but it's really about what I think about quantum mechanics. And it's something that I've grown more and more certain of, that it's epistemologically sound, and it's fairly self-evident, the basis of what I've been thinking, the more and more I work with quantum computing, because the more I work with quantum computing, the more I'm being forced to actually learn the math of quantum mechanics and learn how this actually works from the orthodox point of view. And I don't see I see that what I'm thinking seems to elucidate some dark corners, like of dark matter and stuff like that. And it's basically these three principles. So I'd restate the third one, and I think that they're unarguable. But they lead to certain conclusions. So you can judge for yourself how unarguable they are. That the physical universe is infinitely subconstituent. Any layer you look at, there's stuff it's made of, you know, whatever it is. And it looks more and more like that the deeper they get into particle physics and stuff like that. They try not to look below the level at which we've we have math for, because it disturbs the math. But there it is. It seems to be self-evident and apparent that the universe, as far as we can see, is infinitely subconstituent. There's stuff is made out, little fleas upon the fleas on their backs to bite them. That the physical laws that we use describing the action of familiar forces, classical physics, the reason it doesn't apply nicely to quantum mechanics is that it's huge statistical approximations, the ultimate, the final velocity and things like that. They're huge approximations made up of, a huge number of factors. Everything, and when you get right down to it, I mean, I'm kind of jumping ahead a little bit. The speed of light, transluminal communication. Well, transluminal is how fast the things we regard as made of particles can travel. But what are particles made of, and what's the communication there? Suppose that particles are not things but disturbances of an ambient medium. That, like a photon or a proton is a hurricane. It's a disturbance of the subconstituent medium. That takes a long time to think through, but if you see that, it sort of explains a lot of things about why things like some of the parts of relativity may not apply to everything in the physical universe. They may just apply to things that are on the scale that we're looking at, like the movement of photons and things like that. And that, but the main thing that defeats people is the main thing that defeats people who've tried to restore what they call local reality. The famous physicist. There's a story in the New York Times today about this famous physicist who's trying to restore local reality. So I'm not alone. There's other cranks with many more degrees and much more respect in the field than me. Who's just a kook from the outside coming in and critiquing this. But the paradoxes, like I said, I view what I'm saying as epistemologically sound, and it should that epistemological meaning how we know what we know. Paradox always arises as a matter of perception. It's always that there's an assumption in your perception that doesn't match the truth in your interpretation of your perception. Perception being an interpretive act and not just the raw input of energy into your cornea or something like that. That in perception, paradox arises in perception. And the paradoxes of quantum physics arise, I say, from viewing entities that are disturbances in a subconstituent medium as if they were things. You can look at a hurricane and say, look, there's a hurricane. A hurricane is 600 quadrillion atoms in disturbance, and the disturbance is moving, but the atoms it's made of may not be moving. They may be staying there, and they were disturbed as the disturbance went by, but the atoms of oxygen and nitrogen that were in the air and H2O, the molecules that were there that were part of the disturbance a moment ago, were left behind when the disturbance moved. And I think that this explains, without going into gory detail, a lot of the paradoxes that have been observed in quantum mechanics. And so I just say this to anyone who will sit still long enough to listen, because, it may be one of those things, I may be dead 30 years and will say, oh, geez, this guy was like talking about this stuff. And now we figured it out. And he didn't know what he was talking about because his math wasn't good enough to actually express it in a way that made any sense to anybody. But he kind of did see intuitively what the situation was. And we got down to the next level of quantum physics by making the same conclusions, making similar conclusions. So that's my big spiel for today. I see there's stuff in the chat. I don't know, is this questions or anything like that? Let's see what's chat. So anyway.
Andy, did you mean to ask something?
Hello.
Me?
Yeah.
Not particularly at this point. I jumped in
okay. So
kinda
just
late,
mute then. Just mute then. Just mute then.
Okay.
So.
All right. Anybody with any questions? Now's the time.
And about, go ahead.
Stan Golding, what does hardware look like in quantum computers?
That's very interesting. There's lots of good pictures of it. if you type into Google IBM Quantum Experience, you can get to their thing and you can go look at a bunch of stuff. But basically, it looks like a gold chandelier because it is lowered into a containment vessel so they can cool it down in 2 or 3 steps using liquid helium down to close to absolute zero, because these are because IBM is doing superconducting transmon-based quantum computing. A transmon is a device made out of Josephson junctions. Josephson got the Nobel Prize for suggesting these way back. They're anti-transistors. They're 2 layers of superconducting material with non-superconducting material between them. Below a certain temperature, the superconducting layers are superconducting. They're effectively a voltage to frequency converter. You increase the voltage on one side and the frequency of the waveform on the other. Things cool down until the electrons line up, and they do like a Radio City Music Hall kick dance in synchronization. So the solution to the Schrodinger equation for one of them is the solution to the Schrodinger equation for all of them when they're in this state. And so you get, if the state is pure. And of course, the guy who really brought this along is John Martinez of the University of California, Santa Barbara. And the Martinez group was his group there. And eventually they got conscripted by Google. And so they kind of own the Martinez group now. But Martinez was the first guy I talked to that made me believe that quantum computing was really going to happen. I interviewed him for Dr. Dobbs, and he was the first real, the rest of them were like, geeks in lab coats with dye lasers smeared all over their coats, and they were having a lot of fun playing with quantum computing. They were like shooting lasers through prisms and mirrors at beryllium atoms and a little slot inside a circuit board, and they were bumping 2 beryllium atoms together, and they'd get entangled, and they'd do a simple 2-qubit computation, and they thought this was great. That's still around, by the way, that ion-based, there's a company called IonQ that is doing IonT that is doing ion-based quantum computing. And there's a back end for Qiskit to it as well. That's okay. But what John Martinez of the Martinez group did was he said, we're going to use transmons and we're going to make this work. And damn, when you start doing this, you find what he called the Hamiltonian of dirt. The Hamiltonians are the equations that describe the qubits, and the Hamiltonian of dirt, he called it, was that when you actually did it in the real world, you found out there was an awful lot of stuff they didn't tell you in the textbooks. And that's when I knew quantum computing was going to happen, when somebody was there who understood that. Thank you for the time, gentlemen.
Bill, did you have something? Bill Ragsdale.
Yes. How do people like those 1,500 people at the conference, how do they get to interact with quantum computing? That is this like sending in a card deck somewhere?
Yeah, it's a JSON document, just like any other web service these days. It's a REST-enabled web service, and you can sign up for it by going to IBM Quantum Experience and getting a password. Basically, you just sign up for it, and you have access to real quantum hardware. They have a graphic composer there. You can sit there and experiment with graphic composer, experiment to your heart's content, make quantum circuits, execute them. They run them against the real processors for 1,024 shots each circuit. They show you the results. The results are saved. You can get to them through a web interface. It's a fabulous web service of experimenting with quantum computing. IBM opened it up to the world with the idea that they couldn't pay enough researchers to look for quantum algorithms as they could get for free if they just opened it up for free. So they opened it up for free. They got the open source religion back in the 90s with Apache. That's what changed IBM's attitude towards open source. Long before Microsoft understood it back in the 90s, IBM ported Apache to the mainframes and stuff like that. So they understood if you want people to work for you for free and figure out problems when you're doing a build it and they will come, there's no better way to do it than opening up to the world. So it's all there. And after you get tired of using the composer, you can use the Python Qiskit, which is open source, to write programs to compose computations and transmit them, which is what I do. I play with the composer too, especially when I'm doing demos or something like that. And also if I just want to check something, I'll use the GUI composer online, but most of the time I'm just writing Python code.
So what's
Okay.
typical input and typical output?
Of a quantum computation?
No, from a user standpoint. In other words, if you're sitting in front of your computer screen, what do you put in to interact with the device, and what do you get back out?
Well,
Are you talking text, pictures, lines, numbers, formula?
Well, if you do it with the GUI interface, you do it with, let's see, I think you probably have, let's see, IBM Quantum Computer, Quantum Computing IBM, IBM Q Experience. Yeah, okay, hold us in. Oh, it doesn't know me. Okay, I'll use the other. Hold on, I'll use the other browser. I have 2 browser sessions up. I'll just show it to you real fast. It's real simple. Here's my old Dr. Dobbs articles. IBM Q Experience. Here we go. I'm probably already logged in. I'm not logged in. Come on, stupid thing. Mainframe-based authentication, you know, for the. Okay, so here's the titled experiment. Here's quantum phase experiment 1. Okay, so here's the experiment. It has 1 qubit and 1 classical bit that the output is going to be measured on. You guys could all see this, right?
You can see it. You've got to share screen at your end.
Oh, I thought I had already done that. Okay, just have to. Okay, here we go. Now, can you see it?
Yes.
Here's an experiment. Here's a Hadamard gate and a barrier. Here's a T gate and a barrier. Here's a Hadamard and S dagger gate and then a measurement. Okay, I can run it. Okay, when I go to run it, I can use the simulator or I can use this processor. These are real processors here. Let's say IBM Vigo. Okay, let's see. That says it's got 5 jobs waiting. Let's see, 5 jobs. Oh, no, that's me. It's telling me I can do 5 more jobs like this. It'll run this circuit 1,024 times, and then it will give me the statistics on how it ran. Okay, so I sent it to IBM Q Vigo a few seconds ago. Now it says validating, transpiling, validating. It's not in the queue yet. Let's see here. Transpiled circuit looks like this. This turned into a U2 gate, a U2 gate, a U2 gate, and a Z. That's what these 4 operations got transpiled into.
Transpiled.
You know,
transpiled. I love transpiled.
Yeah, that's right. It's like, it sounds like you're doing it, shoveling it higher and deeper, doesn't it? Okay, it's now queued. Okay, it may be running. Let's see. It says its status is queued. So we go back to the composer. Where's the? Oh, and here. If you express this in OpenChasm language, this is the expression of that circuit in quantum assembly. It's called. Like I said, it's really quantum microcode, but they call it quantum assembly. So I had H the Q. I had 1 register, a 1-bit Q register, 1-bit classical register. I H'd the Q, which is assumed to start in the 0 state, the relaxed state. It is a axiom of the quantum computers that the original state is the totally relaxed state. All qubits are 0. So I H'd the Q. I put a barrier, which is just a transpiler instruction. I T'd the Q, and then I H'd the Q, and then I S-daggered the Q, and then I measured the Q to the C, to the classical bit. And here's what that turned into transpiled. This was H. This is the H. Here's the T. Here's the second H. And here's the measure operation. Okay, so let's see. Let's go back to the diagram and see how my circuit is doing. Did it run? Let's see. Let's go back to. Let's close this and go back to the. Let's see if we refresh it here. Seems to be queued. It may be running, and it may run in sometime, but I don't see it. It says it's queued. It's possible that processor isn't running right now. Sometimes.
That's good. That's enough. It truly is interactive. That's really good. Thank
Yeah,
you.
it's a masterpiece of web programming, among other things. And of course, the documentation, which is all here. This Qiskit notebooks, this Jupyter notebooks I was telling you about. You can
Mhm.
go here and run your way. Yeah, and you can compose them yourself. It'll actually let you create new notebooks. So
I found it's mostly not working. And you got to understand, this is something that, as you say, gets dunked in liquid helium. So it's not that they do 24/7 uptime.
Oh yeah,
I
well,
mean,
there's a Slack channel where you go talk to me. And besides, it tells you if it's running. I just didn't look. See, when you start here's what's going on. Okay, so I put that in Vigo. It says there's 7 jobs in the queue. So I'm just at the end of the queue is what it is. Here it is right here. This is that information. So let's see. See this. Here's my job. It was queued 3 minutes ago. It's in queue position 5. Here it is right here. It's in queue position 5. It'll run in 16 minutes. You'll have forgotten that I showed it to you in 16. But the computer,
Okay, that's enough. That's enough. Let's charge forward. Thank you.
oh, very good. So let me stop share. There we go.
Okay.
Truly a window into another world.
It's a window into our world at a different level. I believe it will transform our perception of our world as much as the digital binary computer has transformed our perception of the world. When fully distributed, when Prometheus has brought the fire down from the heavens.
That's wild. What's
Have
your
you read-
background?
Mine?
Yeah, I love your background image. Where'd you get that?
Oh, I don't know. It just comes on the Mac. You know, if you zoom on the Mac, it just comes with it. It reminds me. I don't know. It reminds me of the view of Mars that they had when Dr. Manhattan takes the Silk Spectre to Mars in Watchmen. But I don't think it's from that. It's from some other. It's from some weekly TV show about living on another planet or something. I've heard it's from an animated show.
So, Jax, if you were going to get started with this, is there an easy resource getting started with Qiskit?
Oh yeah, if you're going to get started with quantum experience per se, just go to the quantumcomputing.ibm.com and play with the composer until you want to know more. There's tutorials, there's all kinds of stuff. You can amuse yourself there. I spent a year looking at that before I actually got involved with Qiskit per se.
Okay, so folks that are interested in doing that can contact you directly on that subject. And on that cheerful note,
there's a Slack.
There'll be a short tutorial now before we have our next speaker. In order to change your name on the screen, if you're so inclined, you get into speaker view.